The concept of demand elasticity, a powerful tool in economics, tells us how responsive the quantity demanded is to changes in price. We measure elasticity as the ratio of the percentage change in quantity demanded to the percentage change in price. If we let delta represent change, the formula for elasticity becomes clear. Using calculus, the demand elasticity at a particular point on the demand curve equals the slope of the curve multiplied by the ratio of price to quantity. In simpler words, elasticity equals slope times price over quantity. It tells us how sensitive buyers are when prices move. If demand is elastic, even a small price change makes people buy a lot more or a lot less. If demand is inelastic, even a big price change hardly affects sales. So, elasticity isn't just about the direction of change, but about the size of the reaction.
For businesses, elasticity lies at the heart of pricing decisions. If a product is elastic, raising prices risks losing customers and revenue. But if it's inelastic, firms can raise prices and still keep most of their sales. Think about it. Dining at a luxury restaurant is elastic. You'll skip it if it becomes too expensive. But salt, even if the price doubles, households still buy it. Governments also care. Taxes work best on inelastic goods because people can't easily cut back. That's why petrol, tobacco, and alcohol are taxed so heavily. Elasticity also matters in international trade. Countries exporting inelastic goods like oil enjoy more stable revenues, and whether a currency devaluation boosts exports depends directly on how elastic foreign demand is. For consumers, elasticity reflects how much choice we really have. Soft drinks, with endless substitutes, are highly elastic. Life-saving medicines like insulin are inelastic. People must buy them regardless of price. Here's a simple way to picture it. Imagine demand as a spring. A stiff spring, inelastic demand, barely moves no matter how hard you pull. A loose spring, elastic demand, stretches easily even with a small tug. And the big takeaway, elasticity isn't just theory. It guides businesses setting prices, governments designing taxes, economists forecasting policies, and consumers making choices. In short, elasticity connects economic models to the real-world decisions we face every day.
Consider a linear demand curve, where price as a function of quantity is given by P of Q equal to 20 minus 2Q. At the midpoint of this curve, when quantity is 5 and price is 10, the elasticity of demand is exactly unitary. Portions of the curve to the left of this point are elastic, while portions to the right are inelastic. Let's explore why this happens. As illustrated in the diagram, for quantities to the left of the midpoint, marginal revenue is positive and total revenue is rising. In contrast, for quantities to the right of the midpoint, marginal revenue becomes negative and total revenue begins to fall. Analytically, demand is given by Pi of Q equal to a minus Bt, where both A and B are positive. From this, elasticity becomes A over BQ minus 1. Total revenue is a Q minus BQ squared. To maximize revenue, we take the derivative and set it equal to 0. Solving, we find Q equals A over 2B. Substituting this into the elasticity expression shows that total revenue is maximized exactly where demand is unit elastic. For our example, let A equal 20 and B equal 2. The revenue maximizing quantity is A over 2B, which is 20 over 4, or simply 5. At this quantity, elasticity is equal to 1, and total revenue reaches its maximum. We can see price decreasing linearly with quantity, while total revenue takes the shape of an inverted parabola. The blue dot marks the peak of revenue, where elasticity is exactly 1. To the left of this point, elasticity is greater than 1. That is, the elastic region of the demand curve. To the right, elasticity is less than 1, the inelastic region of the demand curve.
Consider the nonlinear exponential demand curve. P of Q equals 50 times exponential of negative 0.2 Q. That is, e raised to the power negative 0.2 Q. This demand curve can also be divided into elastic, unit elastic, and inelastic regions. However, the point of unit elasticity is not necessarily the geometric midpoint of the curve, as it is in the case of a linear demand curve. Again, unit elasticity occurs at the quantity where total revenue is maximized and marginal revenue equals 0. The demand curve is elastic to the left of this point and inelastic to the right. Analytically, as shown here, demand is given by P of Q equal to constant A, times exponential of negative parameter C times Q, that is, e raised to the power negative C times Q. Total revenue is simply price from the demand function multiplied by quantity. To maximize revenue, we take the derivative and set it equal to 0. Solving, we find the optimal quantity equal to 1 over parameter C. Substituting this into the elasticity expression shows once again that total revenue is maximized exactly where demand is unit elastic. For our nonlinear example, parameter C equals 0.2. The revenue maximizing quantity is 1 over C, or 1 over 0.2, which is 5. At this quantity, elasticity equals 1, and total revenue reaches its maximum. Whether the demand curve is linear or nonlinear, there is a close relationship between marginal revenue and elasticity. Let's explore this in general functional form. Let price be P of Q, so that total revenue equals P of Q times Q. Marginal revenue is the derivative of total revenue, which gives P of Q plus Q times the derivative of P of Q. Elasticity is defined as the reciprocal of the slope of P of Q multiplied by the ratio of P of Q to Q. With this definition, marginal revenue can be rearranged as P of Q multiplied by the term 1 plus 1 over elasticity. From this expression, we see when marginal revenue is 0, elasticity in absolute value equals 1. When elasticity is greater than 1 in absolute value, marginal revenue is positive and total revenue increases. When elasticity is less than 1 in absolute value, marginal revenue is negative and total revenue decreases. This relationship is general and does not depend on the specific functional form. The exact location of the unit elastic point, however, depends on the form of P of Q and its parameters.
Finally, consider a special case of nonlinear demand called the rectangular hyperbola, given by P of Q equals constant K divided by Q. This is a demand curve that is unit elastic everywhere, for all quantities. Why? Because elasticity is equal to the slope times price over quantity. The slope here is minus K over Q squared, which makes elasticity exactly 1 at every point. Total revenue is simply price from the demand function multiplied by quantity, which simplifies to constant K across all quantities. This is a very special and important case. The demand curve is everywhere unit elastic, and the total revenue curve is perfectly flat. For example, if constant K equals 50, the rectangular hyperbola is shown. Notice that total revenue is a horizontal line. Revenue does not change with quantity. That makes sense because unit elasticity means the percentage change in quantity exactly offsets the percentage change in price.